All right, let's talk about chemical reactions. In a chemical reaction, what you typically have is a set of molecules or elements to the left of an arrow, and then you have elements or molecules to the right of the arrow. And the big A, the capital A, B, C, and D here basically represent molecules. Now, the way you read this is the same way you read most anything else. You read it from left to right. And the big A and big B represent what we call reactants. Anything to the left of the arrow is your reactant. Anything to the right of the arrow is what we call the products. And little a, little b, little c, and little d is what we call the balancing coefficients. They're actually numbers. Numbers that will make sure that you end up with the same number of atoms on both sides of the equation because, as you may recall from our second lecture, we have to abide by the conservation of mass. Whatever mass we start with is the mass that we gotta end up with. And a corollary of that is to say that whatever amount of carbon you start with is the amount of carbon you're going to end up with, or whatever element you're dealing with. So the balancing coefficients will ensure that on both sides of the equations you have the same amounts of atoms or elements present. Another thing that we're also going to be using and categorizing in this lecture is the state, the physical state of the substance. Some of the substances are solids, some of the substances are liquids, some of them are gases, and so we basically depict that by using the subscripts parentheses S, parentheses L, and parentheses G to depict those particular states. And in addition, we also use parentheses AQ, which stands for aqueous, also known as something dissolved in water. And a lot of the substances we're going to talk about in this class do dissolve in waters. There's some that don't, but the idea is that if it does dissolve in water, we have to depict it with the AQ symbol. That's going to have some consequences in terms of the balancing equations that we're going to look into a little later. All right, now, in terms of making solutions, you could actually make solutions with water with most any type of solute. The thing that you're dissolving in it could be a solid to begin with, or it could be a liquid, or it could even be a gas. And as long as it dissolves in the water, you have created an aqueous solution, your AQ symbol, right? All right, we're going to get to that in due time. Now, let's talk about this business of balancing equations. On the one hand, you could look at this equation and balance it by a method known as inspection. In a little bit, I'll show you how you can balance it algebraically. And at that point, you decide which method you decide to stick with. But pretty much what we do is we narrow down on the elements. And what you basically want to see is, or the way you want to start is by looking at elements that are present on only one molecule on either side of the equation. So if you look at this carefully, carbon is only present in the first molecule on the reactant side. And on the product side, carbon is only present on the first molecule on the right side. So that specific atom is only present once per side of the equation. So that might be a place where we want to start with the balancing process. The other molecule or the other atom is hydrogen. Hydrogen is present only in the first molecule on the left side and is only present on the second molecule on the right side. So once again, present only once per side of the equation. On the other hand, chlorine is present in one molecule, Cl2 on the reactant side, but it's present on two molecules on the product side. So that one, because it's present in more than two molecules overall, you want to leave it until the very end. You don't want to start messing with it in terms of the balancing. So looking at carbon, we have one carbon on the left side. On the right side, we have one carbon. So that's balanced to begin with. Now let's take a look at the hydrogens. We have 4 hydrogens on the reactant. We only have 1 hydrogen on the product. So what we're going to need to do is put the 4 in front of the hydrogen. Oh, and by the way, notice what I had right here. I'm saying that the Cl is going to be left until the very end because it's present in more than just one molecule per side. But anyway, we put the 4 in front of HCl, and that ensures that we have now 4 hydrogens. Now what happens is that the carbon is balanced, the hydrogen is balanced, so we need to look at the chlorines, what's happening to them on the product side. And the idea is that the subscript tells you how many molecules, how many chlorines you have in the molecule. But the balancing coefficient tells you how many molecules you have. So here you have 4 chlorines in CCl4. You only have 1 chlorine in HCl. but you have 4 HCl. So in reality, you are dealing with 8 chlorines altogether on the product side. And so what that means is that to balance the chlorines here, you will have to multiply Cl2 by 4, because the 4 and the 2 get multiplied together to give you 8 chlorines altogether. All right, so this is how we balance it by inspection. There's another method to do it, and for this equation in particular, it's going to look super convoluted and kind of pointless. Um, and you'll be right. This equation by inspection is a lot more simplistic and a lot more to the point. But there could be some equations, in particular decomposition equations, where trying to balance an equation by inspection could be kind of hard. And the way you can maybe go around that problem is to balance it by algebra. Now, specifically, what you do is you input balancing coefficients that are pretty much letters, right? They're variables. You don't know what they are, but you know they have to be there. And so our task is going to be to find out algebraically what the value of A, B, C, and D are in each, in each one of these processes. And what you do is you balance. You basically look at it from the point of view of the elements. You have carbon, which has to be balanced on both sides. So that means that A, which is the balancing coefficient, times the one carbon, that's what you have on the left side. On the right side, you have carbon multiplied by C. So A have to equal C if this equation is to be balanced. From the point of view of hydrogen, you have 4 hydrogens in the molecule, but the molecule is multiplied by a balancing coefficient of A. So on the reactant side, you have 4A for hydrogen. And on the product side, you have 1 hydrogen multiplied by D. So 4A has to equal D. That has to be true, or else you will not be able to balance the hydrogens. And then for the chlorine, we have 2 chlorines multiplied by B, that's on the reactant side, and that has to equal 4 chlorines multiplied by C plus 1 chlorine multiplied by D. So that's from the point of view of chlorines. So now what you do is you notice that, okay, you have A in the first equation, you have A in the second equation, you don't have A in the third one, but because of the relationships, you could actually substitute C and D in terms of A. And if you do that, right, so you're going to end up 4C becomes 4A since A equals C. And then your D equals 4A. So you have one D in there, so that's going to also be 4A. So your 2B ultimately equals 8A. And the reason why you want to do this is because the moment you set up the equations to equal one of the variables, in this case, they all equal A multiplied by some value, here you make a very crucial assumption. You assume that A is 1, all right? And by letting A equal 1, you're going to reduce this set of unknowns to equations that will reduce down to just 1. All right, so, or just one variable per one unknown, or per one equation. So if you let A equals 1, which is the common thing in each one of these equations, automatically B becomes 4. Automatically C becomes 1. And automatically D becomes 4. And like that, you have found out the balancing coefficients for the equation. So like I said, it's a little bit more convoluted and troublesome for this specific example, but for examples like decomposition and even synthesis, this might be the way to go, especially if the equation is kind of long and you have multiple atoms in multiple molecules throughout the equation. So just be aware of this method. I'm not going to force you to solve the problems this way, but be aware that there might be some cases where you'd be better off doing it this way than the other way. Whether you decide to use this method or not is totally up to you. All right, so let's talk about synthesis and decomposition really quickly before we end this video. All right, so synthesis reactions, by definition, are those where you start with multiple reactants and you produce only one product. Now, that's not to say that you're going to get 1 mole of that product. The coefficient, lower C coefficient here could be any number. This could be 2, 3, 4, what have you. But you will only have one type of molecule or one type of element present as the only chemical species on the product side. Typical example, iron plus oxygen undergoing basically oxidation, turning into rust, specifically iron 3 oxide. Only one product, so this is technically a synthesis reaction. All right, so by inspection, what you can see here is that, okay, you have one iron on the left side, and then you have one iron located on the product side. Well, technically, you only have two irons here and one iron on the left side. What that basically tells you is that you have to multiply the irons by 2 to make it work out. But before we do that, take a look at the oxygens. The oxygens are not balanced. You have 2 oxygens on the left side and you have 3 on the right side. Whenever you have this even odd um, assimilation between them, what you need to do is cross multiply. So notice here that you have 3 oxygens, you want to multiply that entire molecule by 2. Here you have 2 oxygens, you want to multiply the entire molecule by 3. And you end up with the following situation. Now this ensures that you have the proper number of oxygens. By cross multiplying the molecules with their coefficients, you have ensured that now you have 6 oxygens on both sides of the equations. But now you have changed the iron somewhat. Now you have 2 times 2, which is 4 iron. So what you need to do is place 4 in front of iron. And the moment you do that, you have balanced the equation. All right, so once again, synthesis, only one type of product. All right, now decomposition in a way is the opposite of synthesis. You start with only one thing, but you end up producing multiple products, right? In that respect is literally the opposite of synthesis, but not necessarily the reverse of synthesis. It's just the opposite of it by definition. One reactant, multiple products, decomposition. Multiple reactants, one product, synthesis. All right, so let me show you an example. We have KClO3 turning into KCl and O2. All right, once again, we have that even odd business for oxygen, right? So 3 oxygens on the left side, 2 oxygens on the right side. So you might actually want to balance the oxygens first by cross multiplication. The 3 will go in front of O2, the 2 will go in front of the KClO3. All right, that balances the oxygens. Once again, we have 6 oxygens on both sides. But now that you place the 2 here, you have changed the amount of potassium and the amount of chlorine. Now you have 2 potassiums and you have 2 chlorines. So to balance this, you need to put a 2 in front of the KCl, and that basically balances your decomposition reaction. All right, now as I implied in the previous discussion, it is during synthesis and decomposition that if it's long enough and you have enough products or reactants, you might need to use algebra to solve for it. It's not to say that you cannot solve it using the method of inspection, but it depends how good you are at inspection versus how competent you are at algebra. That will decide whether you want to go one way or the other. All right, now with all that being said, we're going to stop right here, and in the next video we'll talk about combustion reactions.